we should start now. It's Math 1151. We're doing chapter 5.1 and 5.2. That's the beginnings of integration. By the way, can anybody tell me what an integral is? What is an integral? You're fired. Yeah, that's what an integral is. Oh, I remember. That's not so bad. I'm sorry. I apologize for firing you. You're not fired. Rehired. What'd you say? It's signed area between the curve and the x-axis. That's what an integral is. And as part of, so integrals compute signed area. Integrals compute signed area. What do integrals do again? They compute signed area. That's right. They compute signed area. And I see it as a machine. It's a machine that computes signed area. How? I don't know. It just does. And remember, we have some notation. It looks like this. You have the integral. You have the d. Right? This is all one piece. And then the other piece is an f of x. This is the curve that you're looking at. This x here is the variable in question. And this a to b, these are the limits of integration. You go from a to b. This is your integral that computes the signed area. Now, one of the things we did last time is we started computing some simple integrals, like some that looked like this. They looked something like. They did not look like this. I'm going to make something up that didn't happen. So if here's my line, and here's, say, 4, and here's -3, if I was computing this integral here, it would look like, the areas would look like this. The negative area would be down here, and the positive area would be up here. And to me, it looks like there's more negative area than positive, to me, in this picture here. So the integral will be slightly negative, I'd say. Okay, great. So we started talking about how to just use geometry, high school level geometry, to compute these integrals if we know the shape of the curve really well. But the question came up, what if you have something like, well, this came up last time. I remember. I didn't even watch the video. But I remember this question came up. It says, what if you have something like x squared? You have, that's not how you write x squared, Bart. What's wrong with you? Okay, you have x squared. And now we have, and say we integrate from, well, I don't remember what I picked last time. But I'll pick -1 to 1 this time. I think it's good enough. And we have, this is negative, we have positive area here that the integral is computing. That is the positive area computed by the following integral. It's a positive area computed by the integral of x squared dx from -1 to 1, right? And we talked about ways that you could probably get your hands on this area. And there were a couple ideas. One was maybe you could make some various triangles in here. That's a good idea. The idea that I threw out there was just fill the plane with dots and count how many are inside the area, how many are not, and then you could get a good estimate on the area. This is a real way to do it. But then somebody said, well, what if we made little rectangles? And of course, that's, for those who already know the answer of the end of the story, that's what we end up doing. We end up making little rectangles here, little rectangles, and adding them together. And then we make the rectangles thinner and thinner and thinner. That's the strategy here. Okay. But along the way, we need to remember summation notation. And so last time I wrote these formulas on the board, and one of you asked me the very great question, do we need to know these formulas for the test? The answer is no. Great. Yeah, I don't need to know the formulas for the test. These formulas, these three that I wrote, you don't need to know. Here's one that you should know. You kind of have to know this one I'm about to write down, but it's not hard. Okay, let me just, I'm scared. Oh, yeah, it's okay. Okay, so this one's easy. The sum of k equals 1 to n of c, where c is a constant. Now, what does this mean when I write this? I'll do a simpler example and see. So I'm going to take the sum from k equals 1 to 3 of c. So what do? I say, OK, k equals 1. What am I adding together? C. So I put down a c. And I go up here and say, now k equals 2. So I go down here, k equals 2. So now there's my second c, right? And then I say, oh, k equals 3. There's my third c, right? 3 constants in a row. What happens? What's c plus c plus c equal to? 3c. 3c, there it is. And so this is always equal to n times c, because you're just adding the constant to itself n times. That's not hard, right? That you should be able to do. I think that makes sense. And in fact, probably, basically the way this usually comes up would be something like this. This is also very common. This is equal to, I can factor out a c. I can factor out a c, right? So if I have 3 c's here, can't I make that a factor? 1 plus 1 plus 1. Can I factor out that c always? I can factor out the c. And so the c can come outside. And so then that's the c, the sum from k equals 1 to n of 1. And if I add 1 to itself n times, what do I get? N. And so that's a c times n. It's the same thing. I just did it a slightly different way. This is how, these are the tricks that we do with sums. We'll bring this up again, I think. All right. So integrals, compute, signed, area. What questions do you have so far? Oh, sorry. You can just shout it out. That's a great question. She says, what happens if you've always been starting with 1. What happens what is the sum of k equals 0 to n of the number 1? What's that equal to? Okay, we got some good answers here. We got 1 and 2, but no, was it what? N plus 1 is the correct answer. Because what you do is you go through, you say k equals 0. Let's do an example. Let's do a real numbered example, all right? So I'll put a 3 up here. So k equals 0. So I start here, I'm like, k equals 0, 1, 1. Go up here, increment k, okay? K equals 2. Put down my next one. Oh, sorry, k equals 1. We started at 0, and now we're at 1 here. K equals 0, k equals 1, plus 1. This is k equals 2, plus, and this is k equals 3 here. So we get 1 more when we start there, right? Yeah. Yes. So she said this. Well, let's double check that this is right, but I'm pretty sure that this is going to work. She suggested that you have, she said, isn't it true, Bart, that k equals 30 to n of 1, is equal to the sum k equals 1 to n of 1 minus the sum k equals 1 to 30. And how would we, okay, so she comes up to you and she asks you this question. Okay, how would you confirm or deny her question? You guys, it's within your grasp, for sure. You try smaller numbers. You just try smaller numbers, and then you write the thing out, and then you make sure that it works out. So let's see if it's true. Let's see if it actually works, because there's going to be a little issue here, and I want to see if it works. I want to know. Maybe you guys don't want to know, but I want to know. So here we go. We're going to do the sum k equals 2 to 3 of 1. All right? Now this is equal to, so k equals 2, I get 1. K equals 3, I get 1. Do you guys agree with that? I think that sounds right. 1 to 2, it should be 2. Yep. Okay. So now let's do the sum of k equals 1 to 3 of 1 minus the sum k equals 1 to 2. Right? That's what we suggested here, right? Okay, what's the sum of 1 to 3 equal to? 3. What's the sum of 1 to 2 equal to? 2. This is 3 minus 2 equals 1. Oh, guys. Sorry. So did it work? Did I make a mistake? What happened? What? This one equals 2. 3 minus 2 equals 1. But when I go from here to here, shouldn't I get 1 plus 1 equals 2? You're going to have to, right? So you have to adjust. So this, yeah, so this is not quite right, right? So this should be to the 29 here. And now we're okay. And so now this is sum of 1 to 1 of 1. So now this is 1 and this is 2, and so this is going to work just fine. This is if this is confusing to you, this was also, I mean, this is a fact that we kind of try to forget about. You know, like what is 10 9 8? What's 10 minus 5? Well, 10, 9, 8, 7, 6. 10 minus 5 is 6. Is that right? No, what did I do? Started at 10. And it's the same issue. It's exactly the same issue here. It's where you start counting. Right? And so that's a little confusing. But really, you're not going to be starting too many different places. You might be starting at 0 sometimes. This can happen. And what do you have to do? It's going to be one more, right? So the sum of 0 to 1. Although, what is this? Can somebody tell me this sum? I'm going to ask you one last question of sums, and then we're going to move back to integrals. Okay, this is the last question with sums for now, for at least 1 minute. Here we go. I claim the sum of k equals 0 to n of k squared is equal to the sum k equals 1 to n of k squared. Is that true? Why is that true? So even though this one has an extra term in it, this one starts off 0 plus 1 plus 4 plus 9 plus dot, dot, dot. This one starts off 1 plus 4 plus 9 plus ... So when the k equals 0, maybe something weird happens, right? And then sometimes you're going, this happens a lot, sometimes you want to know the sum from k equals 0, or let's just do k equals 1, to n minus 1 of k squared. The sum from k equals 1 to n minus 1 of k squared. You might say, easy. I have the formula here. So what's the answer to this? Here's the formula. Here's this. Yeah? It's, you know, it is going to be n times n minus 1 over 2, but I'm going to write it as n minus 1 times n. Oh, well, I didn't mean to write the squared. She answered the question that I really meant to ask. Yeah, that's scary. Right? That is the question I meant to ask. And so we just lower this one by 1, lower this one by 1. All right? Does that make any sense? What do you guys think? I lowered this factor by 1, so in the formula it goes to n minus 1, right? And then the n plus 1 goes, yeah. All right. So let's see if we can estimate, a sum using this horrible method. Okay, let's try to go ahead and do this. Let's do this. Here we go. All right. So let's in fact, this is going to be our example. Boy, I hope this isn't a mistake. Let's try to do this. Yep. Let's see if we can work this out. That one seems good to me. So what we're going to do is we're just going to follow our noses and do what the most obvious thing is most of the time. All right? So strategy, make some rectangles. And then, so make some rectangles. Make some rectangles. Now, theoretically, the rectangles can be kind of arbitrarily sized. That's the idea. We're always going to make them equal sized, okay? Just because. So from -1 to 1, how much distance is between -1 and 1? 2, okay? So how about we make 8 rectangles? 8 rectangles. Say, in this case, we're doing this, we're computing the integral from -1 to 1 of x squared dx. That's what we're approximating. We're not actually, we're approximating. And we're going to do it with 8 rectangles. 8 rectangles. And a standard problem would be like, yeah, I picked it. A standard problem, that's a good question. A standard problem would say, approximate this integral using what we're doing here is called a Riemann sum, okay? A Riemann sum, not Riemann, Riemann. So the problem would say, use a Riemann sum with 8 partitions or 8 intervals to approximate this thing. So that means 8 rectangles. Now, let's draw a picture. Let's just think about what's going on. We just think about what's going on, every single question that we could possibly have will basically arise, and we should be able to take care of it. No problem. What? I already have a drawing. I want a better drawing. I want an even better drawing. I know I already have. Thank you very much. That's great. So here we have x and y, and here I have -1 to 1. They say, why is he drawing it again? That's a good question. Do we use the left edge or the right edge? Does anybody else know what he's talking about, or whoever said that's talking about? We have, if we break this into 8 rectangles, how wide is each rectangle? 0.25. Why did I pick 8? Because I took 2 and I said, I want to make a nice number, basically. And so 0.25. And so here we're going to have, oh, geez, Bart. This is going to be delta x, which is going to equal 0.25. It's the width of our rectangle. Now, there's 2 different ways we could draw our rectangle. Well, there's more than 2 even, but there's at least 2. One way is you could have the left endpoint of your rectangle touch the curve. The other way is you could have the right endpoint of your rectangle touch the curve. So I'll draw it with left endpoints. We'll start with left endpoints. So here's my rectangle. I'm drawing it. Let's draw the rectangle with a different color. Let's draw it with purple. The left endpoint, if I have my point, how tall is the rectangle here? 0. That one's easy. 0. It's a flat, arealess rectangle. No area to that rectangle. Here, this is supposed to be there. That's 0.25 squared. And so, see, the left endpoint is touching the curve, right? The left endpoint. When you do a Riemann sum problem, draw a picture. He said, why are you drawing a picture? I couldn't solve the problem if I didn't draw another picture. Left endpoint. Here we go. There's my left endpoint touching the curve. Another left endpoint touching the curve. Those are my beautiful rectangles. All right, so now I'll draw the other one, right? Now I want to have the left endpoint touching the curve. So look what's going to happen. There's the one rectangle, right? Here's the next rectangle. There's the next rectangle. And there's the final rectangle. Let's draw this. Let's just really... There we go. So look, on the right-hand side, we're underestimating the area. Yeah, what's up? She asked, does this overestimation account for the underestimation? No. Yeah. It will kind of account for it a little bit, but there's no reason to think it should. In this case, it will be close, but there's really no reason to believe that they should account for anything, actually. You have some excess, right? You're either under or you're over the actual area. And the idea is, as we take a limit, right? We took limits at the beginning and make the rectangles skinnier and skinnier and skinnier, then this excess, no matter what it is, will go away. For example, I did both sides, but you don't even have to have things canceling out. It kind of does in this problem. And it'll give us a nice estimate. But all right. So that's our rectangle. Now look, we know the formula for the area of a rectangle, right? It's base times height. Base times height. So all we have to do is, well, whatever. All we have to do is write down, well, I can't proceed without making this symbol. So I'm going to write down a sum. There's my big, scary E. The scary E. Oh, it's an S, too. Boy, Bart. Not the best day. Scary S. How can I tell whether or not the rectangle goes over the curve or under the curve? It's the endpoint that I'm making touch the curve. I'm making the left endpoint of the rectangle touch the curve each time. So here, the left endpoint, the left endpoint, the left endpoint, the left endpoint, the left endpoint touches, the left endpoint touches. This left, for this one, and for this one, it's the left endpoint that touches. This is left endpoints. That's how. Did that answer your question? Yeah, good. Okay, so now, I'm going to try to write a formula. How do you compute the area of a rectangle? Should be easy, right? Base times height. Base. What's the base? Delta x. It's okay. The chain. It's delta x, but I'm just going to write 0.25. That's it, right? How many rectangles do I have, by the way? 8. So this is going to be a sum. K equals 1 to 8, right? K equals 1 to 8. 1, 2, 1, 1. Looking good, Bart. Okay, great. Now all I have to do is figure out what this height is. Well, how tall is each one of these rectangles? Here, I'll answer for you if you don't mind. It's f of something. It's something squared. The height is always something squared, right? Because that's what we're doing. We're doing this square function, right? Something squared. All right, so how do I figure out what I'm squaring? Right? Delta x is not squared, all right? Delta x, yeah. How about -1? All right. Let me move very slowly here, okay? You guys are doing great. I understand what you said, and I understand definitely what you guys are saying. It makes perfect sense. And I bet you could even make it work, okay? But if you don't mind, I'm going to write -1 here. That is this -1. That's that -1. And I want, when I plug in 1, I'm going to take this one right here, this thing here, and plug it in here. I want to make sure I get -1 out. So what I'm going to do is I'm going to add it to k -1 plus 0.25 times k -1. Oh, that's wrong. Wait. Is it? Oh, it is right. Woo! Okay. So now, I say this is right, a couple other people say it's right. If you say I don't know, let me see if I can convince you that it's right. Make sure you should understand this. This should not be magic. Okay, this 0.25, that's the delta. So here's how the sum works. K equals 1. What's 1 minus 1? 0. So it's 0 times 0.25. And so then we're at -1. We're right here. That's the height of this rectangle times the width. So first we get the area of this rectangle. And then we add it to, then k equals 2. And k equals 2, what's 2 minus 1? What's 1 times 0.25? So minus 1 plus 0.25 is minus 0.75, right? So then we're here. We're squaring it, and then we're multiplying it by the width. And what happens when we plug in 8 there? What do we get out? When we plug in 8, what's 8 minus 1? 8 minus 1 is 7. 7 times a fourth is 7/4, right? 7/4 is 1 3/4, so we go over 1 and 1, 2, 3/4. This is 3/4 right here, isn't it? Then we square it, and it's the height of that rectangle. Does that kind of make sense to anyone? If somebody has a question, can they ask? And I can try to, all I'll try to do is explain it again. That's all I'm going to try to do. I can also work another example here in a second. Yeah, what's up? Why is it not just x squared? Well, I need these numbers. I need these numbers here to be first, I need it to be minus 1. And then I need it to be minus 0.75. And then I need, because that's this one right here. Right? And then I need this thing inside to be minus 0.5. Then I need it to be minus 0.25. Then I need it to be 0. Then I need it to be 0.25. Then I need it to be 0.5. And then I need it to be 0.75. And I have 1, 2, 3, 4, 5, 6, 7, 8 numbers here. And so these are all plugged into the squared to give me my orange dots here. Does that kind of make sense? Yeah. And you might... That's exactly right. Here's the squared for the... It's exactly what you said. For the x squared, and the number, this formula inside just gives me these numbers. Yeah, what's up? Good question. Okay, so this guy says, so this would give you the answer for left endpoints. How do you do it for right endpoints? Let's do the same problem for right endpoints. So again, the first thing I'm going to do is I'm going to draw a quick picture. Here I go. I'll draw it faster than last time, I think. There we go. We're going from minus 1, because I say so, to 1. And we're going from right endpoints. And I say my delta x is 0.25. There it is. Right endpoints. Okay, right endpoints look like this. I should get the same answer, shouldn't I? For both of them? There's some symmetry here. Oops. There we go. Those are the right endpoints. And what's the sum look like? What did I write down? First I made the big summation sign. What did I do next? Sure, k equals 1. K equals 1, 2, 8. So because there's 8 rectangles, this one counts too. And then next thing I put in is I put the 0.25 in just because I could. All right? And then the next thing I put in was I squared some stuff. This is how I did it exactly last time. And then I said, what has to happen here? How does this work? Well, when k equals 1, what number should come out? Work from left to right. It makes your life easier. When k equals 1, what number should come out? Should be -1 should be put in here somehow. And so what I'll do is I'll do it exactly the way I did it last time, because that's This is the most obvious way to do it. There's this -1. It is that number. You put that number there. And then I'm going to add it to, and then, what? 0.25 times k. 0.25 times k. Boom. There it is. That's it. That gives me right endpoints. Okay, so now, how do you figure out what this is? Geez, you use your calculator. That's what you do. You type it into your calculator, and then you add it all up. All right? That's how you do it. You use your calculator. And should we get the same thing both times? Absolutely. It's very symmetric. All right. So that's not a bad example. Oh, yeah, what's up? Yeah. That's a great comment. That's a really great comment. I'm going to say it out loud to everybody. Okay, she says, Bart, she didn't really say this, but she kind of said this. Bart, I think a much better way to explain this than the way you did is what you do is you think of the k as k equals 1. You're computing the area of the first rectangle, right? K equals 2, 3, 4, 5, 6, 7, and 8. The k corresponds to the rectangle whose area you're computing. Work from left to right. 1, 2, 3, 4, 5, 6, 7, 8. Thank you very much. That's great. That makes a lot of sense. Does that make sense to anybody else? Yeah, what's up? That's exactly right. He said, okay, so for this one, you plug in k equals 1 here, and then you get -1 plus 0.25 is -0.75. And look, how tall is this rectangle here? It's minus 0.75 squared. That's exactly right. Now, let me give you some general guidelines. There's a little trap that I think you might be tempted to fall into, mostly because I've been tempted to fall into it many times, including when I was standing up here 5 seconds ago. I almost went crazy and almost did the problem totally wrong. Almost. Okay, so here's something. One of the things that's maybe kind of bad about this example is I have a lot of 1s lying around. I've got this 1 here. I've got this -1 here, right? You might be tempted to just write -k or something silly like that. That will never work. What you have to do, let's do just another example. If I had, say, I don't know, x cubed plus 1. X cubed plus 1 looks like this. But let's say I wanted to integrate it from 2 to 3. Let's say I wanted to integrate it from 2 to 3. Let's write a Riemann sum with 4 rectangles. And there's only one more way to do this. You have left endpoints, you have right endpoints. Well, let's do it both ways. We'll do it with left endpoints and right endpoints. Okay, so if I have four rectangles, what are the divisions here? If I have 4 rectangles, 0.25, it's still a fourth. It's delta x. This is never the hard part of the problem. At least I don't think so. If we have left endpoints, it's going to look like this, isn't it? And are the rectangles going to be above or below the curve? Below. Below the curve here. So now, You have your sum. How many rectangles do I have? 4. So what's k go from? K goes from 1 to 4. K enumerates, it counts the rectangles. 1, 2, 3, 4. What's the width of each rectangle? 0.25. There, I'm writing it down. We're always doing the sum of length of height times width. Always. Now, I'm going to, let's see. Aha. Now I have to take whatever the height is, and I have to cube it and add 1 to it, right? So now, what is the height of each rectangle? What type of endpoints are we doing? Left endpoints, left endpoints. You always, always, always write in, you always write in this number first. So you write 2, there it is, 2, and then I'll do plus the width, 0.25, times k minus 1. Of course, you can't read that. I wrote it too small. Here, I'll fix it in just a second. Sorry. I'm just rewriting what I just wrote. Two plus 0.25 times k minus 1 cubed plus 1. And we can check it. When k equals 4, what do we have here? When k equals 4, what's k minus 1? 3. What's 3 times 0.25? 3/4, right? Plus 2, that's 2.75. It goes right here. And then we're cubing it and adding 1 to it. That sends you. And then we're multiplying it by the width. It's computing the rectangle. What's up? Yes. She says, okay, you did the left endpoint, k minus 1. You did the right endpoint, no k minus 1. What type of endpoints am I doing here? Left endpoints. Left endpoints. K minus 1. It's the one that shifts you over. It's basically with the sides between the two. I'll go with him first, then I'll call you. What's up? He says, is the 0.25 going to change throughout the problem if delta x is different all the time? Well, we can take the limit as delta x goes to 0. All right? We can do that. And it's not that hard. But in general, if it's delta, it'll either be delta x, or it's going to be some number and it's not going to change. Then that's a different problem. If you're going from 0 to 10, right? It would be 10 divided by 5. So yeah, 2. Your delta x is always the number, it's the interval divided by the number of rectangles. There's one more way this can happen. Instead of doing left points or right points, we could do, did you have a question? What was it? The question will always tell you to use left or right. Or midpoints. Midpoints is the next option. Oh, crap. How do we do midpoints? Let's see. So let's do my favorite example one more time. this time, where do you think the change is going to be when we make midpoints? Where is it going to look different? Yeah, you pointed to here. This thing's going to change. Everything else is going to be the same. Everything else is going to be the same. Let me draw a quick picture of this, and this will be for midpoints. Or midpoints. Here we go. So here's my curve. I'm doing x squared again. Here is -1. Here's 1. I say there should be 8 partitions, 8 rectangles. How wide should each rectangle be? 0.25. It's 2 divided by 8. So 0.25, 2, 3, 1, 2, 3. There we go. And we're putting the height of the rectangles at the midpoints. Oh, geez. So the midpoints, you go here. There we go. There we go. Midpoints. And so here's the rectangle. Here's the rectangle. There's the rectangle. There we go. There, do you see how the midpoint, the rectangle passes through the curve at the midpoint of its side? Does that make sense? The Riemann sum is going to be very, very similar. Personally, I think midpoints are a little harder than the right or left. I hope, I don't know, but I hope that this should ever appear on a quiz that they always ask one of you to do right or left and not some other group of you to do midpoints. Might be unfair. Anyways, we write a sum. How many rectangles do we have? 8. K equals 1 to 8. Okay. It's going to be, the width of this thing is 0.25. Fantastic. The function is squaring. That's nice and easy. Okay. But what am I squaring here? Oh, I start where? Where am I starting at? -1, so I just write -1 here. You always put your left-hand endpoint in that little spot right there. That's what you always do. And now I need to increment this, move over. And I need to make little increments. I need to move this over so that somehow, what do you guys think I do here? 1/2 K. 0.25 times 1/2 K. Times K over 2. Does that work? 0.25 times K over 2? No, that doesn't work. Okay, that's shoot. Okay, so what do I do here? That was a good guess. I wanted to move by half of 1/4. Half of 1/4 is 1/8. So that's 0.125. I wanted to move by that much, and I wanted to start off someplace. Aha! So I should add, this should be -1 plus 1/8, okay? That gets me right here. And now, each time I add an extra K, I want to add a whole another quarter. So that's going to be plus 0.25 times K minus 1. Whew. You might be able to do that without the K minus 1. But class is over for today.